Nothing. So we are. So we're doing week 6 today, and this week we're gonna have an optional lab. So if you if you're kind of falling behind on some stuff, or if there's any like maybe you didn't finish the last week's lab, you can kind of work on that and not do this. But it's a fun lab on diodes and transistors. It's something that we don't cover in circuits in Engineering 12. So if you're a mechanical engineer, it might be your only chance to see this. If you're an electrical engineer, you'll see it in future classes. Or a computer engineer. Also due on, is that Sunday, the March 4th, is the Lab Practical 1. And you might decide to take that in class today, so you don't have to worry about it over the weekend. You have an hour to do it, and you can either do it completely online using Tinkercad, which if you're an online student, that's the way you're going to have to do it. Because I don't want to try to see a photograph of a circuit. It's really hard to kind of always view that properly. But I can see Tinkercad circuits a lot better when you do a screenshot. But if you're here in the classroom and you want to do your circuit problem on a breadboard, a real breadboard, and just have me look at it and check it out in person, you can do it that way in class. So just to kind of show you what the Lab Practical looks like, it is a practical uncovering resistor color codes, determining a value from the colors and determining the colors for a value. There's a chart there. It's real easy. Everybody should get those. But those are only worth it altogether 4 out of the 20 points. The big point is doing a breadboard of a circuit. The circuit has 2 voltage sources and 3 resistors. You have to wire it kind of like the circuit we did last week for nodal and mesh. So that was a bit of a challenge. Had like a floating voltage source. You have to be able to rig that up. And you have to measure voltage and current using the multimeter components in Tinkercad, or a real voltmeter if you're doing it in the lab here today. You have an hour to do it. So you could easily knock that out in the last hour of class if you want to. There is a hint on breadboarding. If you want review, remember the handout for Lab 5, which kind of gave you some guidelines on converting a schematic into a breadboard that sort of more or less lines up with the schematic. So it's fairly easy to do. Also, there is a nifty breadboarding quiz. I was going to actually incorporate this into the practical exam, and I may someday do something like this. This is really, really kind of cool. It's some website where you have a schematic and a breadboard, and you're asked a multiple choice question, which one of these answers is most correct. And you can kind of go down and try to probe that circuit, look at it really carefully, and see which one makes sense. Those of you who are having troubles breadboarding, this could be really, really helpful to kind of straighten out where you're getting some areas confused. There's actually 6 questions here. This is going to probably going to work into a quiz bank later when I have time to kind of process it. But I don't really like the photographic approach because, again, it's a little bit unclear. Some of the circuits are, well, some of the wires, like there's one in particular that's this is why I don't like to grade like actual circuits. If you look at this resistor here, if you can see my little arrow, it looks like it's connecting into that hole right there, but in fact it's circling back and connecting right into that hole. And those are the kind of things that drive me crazy when I'm trying to look at someone's circuit as a photograph. I can't really tell where it's plugged into half the time. And same way, it looks like it's plugged into there, but it's actually circling back and going into there. But it's really, really hard to tell. So, so in order to be useful, you have to kind of do these in something like Tinkercad, so it's clearly indicated where the wires are going. But you can still have a lot of good time just kind of studying this thing and trying to figure out where the errors are or if it's correct. That's just a warm-up. You don't have to do that. The actual test, I will give you an example of what it will look like. It's going to look something like this. These are chosen at random from a bank of questions. You got some resistors. You got to tell what the value is based on the color. You got to tell it what the value is based on the color. You got to change what the color is based on the value. You got to say what the color is based on the value. That's 1 point each, 4 questions. And then something like this, you have to build a breadboard and measure. And there's a bunch of different options for that too. So it's chosen at random, so everyone will hopefully get a different one. And yeah, that's the quiz. That's the test. It's a practical test. It's worth about, I think about 10% of your grade. So do a good job on it. And that is the practical. You can do that today if you want, or you can do it at home using Tinkercad later. Today's lab is optional, so if you just want to do the test today and not do anything else, that's fine too. The topic of this lab is diodes and transistors. Two really, really important circuit components that we are not looking at in Engineering 12. And the reason why we're not, I sort of gather, although when I took my first circuits class, we definitely covered diodes and transistors. But the reason they kind of stand out from everything else we do in circuits is that they're nonlinear. And we were talking just this week about the importance of linearity and how that gives you all these great properties like source transform, superposition, Thevenin equivalence, all those things that we're doing in this week's homework and last week's stems from linearity. You can't really analyze these things the same way. Sometimes if you kind of understand their operating point, you can linearize them. You can kind of just figure out what the slope is at the operating point and kind of think about them as linear devices, but they really are not linear. They're very nonlinear. And you can follow some links if you want to get some more information. But a diode consists of two. I mean, the physics. Actually, you're going to learn more about the physics of semiconductors in Engineering 4. When we cover the electrical properties section, you're gonna really understand how they make semiconductors. What they do basically is you take a crystal of like silicon, and there's ways of doping the silicon so you actually embed like ions of positive charges on one part and ions of negative charges on the other part. And I don't know how that works exactly. Maybe it's just they just stuff a bunch of electrons with a deficit. Anyway, the lattice ends up being sort of N negatively charged and positively charged, and at that boundary, it kind of creates a barrier for the flow of charges across that unless you apply a bias voltage that kind of helps them shunt across. And that makes a diode act kind of like a switch. A diode is just two layers, one of these N layers and one of these P layers sandwiched kind of smacked together. And it provides a simple solid state switching behavior. And if you look at the IV curve of a diode, we're typically, you know, with resistors, we looked at the VI, V on the y-axis and I on the x-axis. With diodes, it kind of makes a little more sense to look at I on the vertical axis and voltage on the horizontal axis. And it's sort of an exponential curve. You can kind of see what happens when you get to the bias voltage. All of a sudden, current just rushes across the boundary. But before you do that, the current is pretty close to zero for a certain range of voltages. And even if you put the voltage in backwards, it's still, I mean, actually, it is basically zero all the way up until you get to a breakdown voltage. And to explain that a little bit more, I probably should, no, I didn't bring mine. What if I do? Oops. So what happens with a diode is, you know, you have this symbol here with the arrow. I want my mouse to get over there. That symbol for a diode has an arrow going in one direction and a bar across it. And what that means is it's going to allow current to flow in the forward direction, but it's going to resist current flow in the reverse direction. And this is the forward direction. So if you have plus and minus a positive voltage VD here, this is what we're showing here. If the voltage across the diode is this way, in other words, charges are losing energy as they're going across from positive to negative. It's a passive component still. There will be a barrier until the voltage reaches this bias voltage, which is about 0.7 volts for silicon or 0.3 volts for germanium diodes. Those are different semiconductor materials you can use. And then once you get past that, it's like a short circuit. So you can kind of model a diode in the extreme case as a an open circuit which has no current flow for a certain range of voltages, and a short circuit which is like a short for past a certain voltage value. And a diode is kind of like a valve in the sense of we have these in our body, in our veins, which kind of keep the blood from flowing backwards when it's kind of like a flap that kind of closes when the pressure goes the wrong way, and when it goes the right way, it lets things flow, and when it kind of flows backwards, it kind of closes. So diodes kind of work like valves that way. They're also very useful in power rectification. You use them to rectify AC voltage. So you have these things called AC rectifier diode bridge, something like that. It goes from AC to DC. You can kind of see how they're used. This is a pretty typical example right here. It's pretty cool. It's called a full wave rectifier. In case you're interested in these are real applications. If you put a sine wave, which is kind of what you would get from a wall, when our power comes off as the wall is AC, alternating current, you can put them in this circuit here, and what comes out from here to here is going to be DC. In other words, it's not going to go negative. It'll be sort of a scallop shape, which you have to sort of filter. But the way it actually works is current, when the voltage at this terminal is positive, at the top is positive, right? The current's going to flow into D1, and it's going to flow into your load. It can't go to D3 because it's blocked that way, right? It's going to flow into your load and out, and then it's going to go through D2 back into the minus sign of that source. When the sign of that thing is flipped, so now the minus sign is short and is on the top, and the positive sign's at the bottom, the current's going to go the other way. But when that happens, it goes through D3 and goes also back into the top plus voltage side of that load. It's a pretty brilliant way of organizing these things so that you always get a positive voltage at V, and you always have the low end potential at this side here. That's a diode bridge, rectifier bridge. Where is my, go over here, there we go. And so what you're going to be doing is you're going to be exploring, basically you're going to be working with an LED, a light emitting diode, which are really common. These are diodes that actually will illuminate when you connect them the right way in your circuit. And you have to connect them in series with a resistor so that you control the amount of current that's going through them. You have to be really careful with diodes, because if you connect them directly across like a 5-volt source, you're going to be in the on range where it acts like a short circuit. And it's going to fry the diode. It'll actually burn out the diode, so it won't actually work anymore. So that's why we use resistors to control the flow of the current, because a 1 mega ohm resistor is going to only let a very small amount of current through. And what we do is we're going to measure the voltage, and we're going to compute what the current is using the nodal analysis formula that the current through R1. What was the current if this node here is VD, the diode voltage, and this node here is 5 volts, what would the current be through R1 using nodal analysis? Typical nodal equation. Mark? Yeah, 5 minus VD over 1 mega ohms would be the current going through the right through that resistor. So you can calculate the current and you can measure the voltage, and then you're going to do this with a few different resistors here. If you change the resistor, you're going to get more current. If you lower the resistor, you get more current. And you do a few points like that, and you know what? My battery's going to die. I got 14 minutes. I should probably run. I was going to go to my office. My power supply is, of course, in my office. I got to go run and get it. But that is the basics of the lab. And then you get to work with transistors, which are other really cool devices. They are actually a PNP sandwich or an NPN sandwich. You have an extra layer of doped material that gives you a 3-wire component that acts like a switch. When you have a voltage across B and E, it allows current to flow from C to E. And you'll get to measure those. And ultimately, you get to make, at the end of the lab, you get to make a dusk to dawn circuit by hooking up a diode, an LED, and a transistor together, such that, actually, this is just an LED circuit. But at the very end, there's an application, if you go that far, for the dusk to dawn circuit. This is a circuit that when you shine light on a photocell, that's a resistor that's sensitive to light. You change the bias voltage here, and you can, when there's no light, you're going to have current flowing, and the LED is going to come on. Like when you have like you have a switch in your house that comes on when the lights go, when it gets dark outside, you have kind of a light that turns on. So when it's dark outside, the LED shines, and when you shine a light on it, you can take your mobile phone or whatever, shine a light on it, the LED will actually shut off. That is a kind of a cool application you can kind of build towards the end of this lab. So it's an optional lab. Have fun with it. I'm going to put my computer to sleep while I go off and get my power supply. Any questions before we get going? Okay, I'll be right back.